Hello everybody and welcome to my video presentation. My name is Sibylle Moehle and I am working at the Institute for Formal Models and Verification led by Armin Biere and at the Lit Secure and Correct Systems Lab at Johannes Kepler University Linz. I am going to present our joint work with Roberto Sebastiani from University of Trento. In this work, we developed a method for enumerating partial models of a propositional formula without repetition. In our approach, logical entailment plays a central role, and our entailment test comes in 4 flavors of different strength. Model enumeration is a key task in various activities, such as lazy SMT, predicate abstraction, software product line engineering, model checking, and pre-image computation. In some applications, avoiding to enumerate models multiple times is crucial. Examples are weighted model counting for probabilistic reasoning in Boolean domains and weighted model integration, which generalizes weighted model counting for hybrid domains. Finding partial models is also relevant in predicate abstraction and pre-image computation. In these models, not all variables are assigned a value, and each partial model represents a set of total models of the formula. If only a subset of the variables is significant, the models are projected onto these relevant variables. Projected model enumeration occurs in existential quantifier elimination, image computation, and bounded model checking. In my presentation, I first motivate the main ingredients of our approach and present our method. After stating the entailment condition in a precise manner, I introduce the 4 flavors of our entailment test by examples and point out future research questions. Our main motivation is given by weighted model integration, short WMI, where the addends are partial assignments satisfying F. In these models, not all variables are assigned a value, and each partial model represents a set of total models of F. Applicability for WMI poses particular requirements. First, the number of addends shall be small, therefore we want our partial models to be short. This can be achieved in several ways. Either by shrinking models, for example by taking into account structural information of the formula as proposed by Tibebo and Fay, or by dual reasoning, where additionally the negation of the formula is considered. The main idea herein is that an assignment falsifying the negation of a formula F is a model of F. Another possibility is to make use of logical entailment. Following Sebastiani, we say that the partial assignment I logically entails a formula F if all its total extensions satisfy F. Notice that I may not satisfy F, nor need its partial extensions satisfy F. However, I represents a set of total models of F. Consider as an example the formula F over the relevant variable x and the irrelevant variable y. The residual of f under a trail I is obtained by replacing the literals in f whose variable or its negation occurs in I by the truth value. If now we set x to true, the residual of f under x is y or not y. It is obviously valid, but it syntactically differs from true. The possible total extensions of x are x, y and x not y, which both satisfy f, and therefore x entails f. But a modern SAT solver does not detect this fact. In the worst case, it needs to assign all unassigned variables before finding a model. In a more realistic example, determining entailment might result in avoiding a significant amount of decisions. But determining logical entailment is harder than it seems. In our work, we chose to test for logical entailment. This test is crucial, and we are going to present it in 4 flavors with different strengths together with examples. Second, to be suitable for WMI, models must not be recorded multiple times, and we therefore target model enumeration without repetition. This can, for instance, be done by adding the negation of the model found as a blocking clause to the formula. The downside of this approach is a potential exponential blow-up of the formula. If a model is found, the search does not terminate, but a decision need be flipped. If no blocking clause is recorded, the formula contains no reason for this flipped decision literal. This may lead to problems in later conflict analysis. Toda and So address this issue with a variant of the conflict analysis procedure. The idea is to add the negation of any flipped decision literal encountered during conflict analysis to the learned clause. The addition of blocking clauses can also be avoided by executing chronological CDCL presented by Nadel and Rivkin, where the solver, instead of jumping to the assertion level, backtracks chronologically. In their work, the authors provide fixes to the invariants considered crucial for CDCL, which are violated. We presented the formalization and generalization of their method together with the correctness proof. Avoiding the use of blocking clauses was a major concern, and in our method we therefore applied chronological CDCL. Let f be a formula over disjoint sets of variables x and y, and assume the variables in x are relevant and the variables in y are irrelevant, that is, we want to project f onto x. We say that we existentially quantify f over y. We want our method to be suitable for applications where not all variables are relevant, such as Bayesian reasoning. So we enhanced our algorithm by projection capabilities, and finally we make use of dual reasoning in some entailment tests. If we combine the found models by disjunctions, we obtain a disjoint sum of products, or DSOP, which is a DNF whose cubes are pairwise contradicting, and which is logically equivalent to f projected onto the relevant variables. Our approach is inspired by how theory and SAT solvers interact in lazy SMT. In this figure, a schema of our method is depicted. The main enumeration engine is a SAT solver based on chronological CDCL. It takes a formula f as input and iteratively builds an assignment I. In every iteration, it checks for units or whether a conflict occurred or a model has been found. Since we are in the context of model enumeration, after having found a model, it also checks whether there are still assignments to be tested. If none of these conditions is met, a decision is taken. But wait, what if the residual of f under I is valid, but syntactically differs from true, like in our example explaining logical entailment? Instead of deciding a variable right away, we test for logical entailment first. Our entailment check comes in 4 flavors, which I am going to introduce next. But first, the entailment condition needs to be stated more precisely. We are given a formula f over sets of variables x and y and a trail I, which represents a partial assignment and ranges over variables in x and y. Checking whether I entails f involves checking whether all total extensions of I satisfy f. Therefore, in phi, only the unassigned variables in x and y are quantified. If phi is true, then the residual of f under I is true for all possible total extensions of I, and I entails f. We are interested in the model of f projected onto the set of variables x, and for each possible assignment jx to the variables in x not occurring in I, it is therefore sufficient to find one assignment jy to the variables in y not occurring in I, such that the residual of f under the resulting total assignment is true. In essence, we need to determine the truth value of the QBF formula phi. However, in some cases a less expensive test might do the job. As already mentioned, we identified 4 entailment tests of different strengths, which I am going to introduce by means of examples. The syntactic check is the cheapest and also the less strong one. It tests whether the residual of f under I is true. If this is the case, then I is a model of f. The quantified entailment condition shown on the previous slide is met, and I trivially entails f as in this first example. Alternatively, if the residual of f under I syntactically differs from true, an incomplete algorithm might be used. Any assignment falsifying the negation of f is a model of f, so we can check whether the formula not f and I is unsatisfiable. We might, for instance, execute only unipropagation or abort the search of the predefined number of decision levels, and this check also might return unknown. In this example, the syntactic check fails, since the residual of f under x1, x2 syntactically differs from true. However, it is valid. Unipropagation is executed on not f and I, and after propagation not y we encounter a conflict. Therefore, not f and x1, x2 is unsatisfiable, and x1, x2 entails f. Our third entailment test consists in running a SAT oracle on not f and I until termination. Modern SAT solvers work mostly on CNFs, so we transform f and its negation into CNFs p and n. For this example, the syntactic and the incomplete check are not strong enough to determine that I entails f. The residual of p under I syntactically differs from true, and the residual of n under I is neither constant nor does it contain a unit. If a SAT oracle is called on n and I, it returns unsat. It is therefore able to show that I entails f. The fourth test is the strongest and also the most expensive one. It captures precisely the entailment condition on the projection and involves a QBF oracle for checking it. In this example, x1 entails f, but none of the checks discussed so far is strong enough to determine this fact. The residuals of p and n under x1 are non-constant and contain no unit, and a SAT oracle called on n and x1 finds a model of n, that is, an extension of x1 which is a countermodel of f. A QBF solver checking phi instead returns true, showing that x1 entails f. There are two things in the paper I left out but want to mention. We started out by adding the entailment test to the standard CDCL algorithm. We then formalized our method. This in particular helped us gaining a deeper understanding of the relevant entailment condition and resulted in the 4 flavors of the entailment test which motivated the title of our paper. Our contribution can be summarized as follows. We developed a method for computing partial assignments entailing a formula on the fly. It is inspired by how theory and SAT solvers interact in SMT, and it combines dual reasoning and chronological CDCL. We further devised an algorithm and a formalization. Our entailment test comes in 4 flavors of increasing strength. The cheapest but also weakest test is the syntactic check. It tests whether the residual of the formula under partial assignment is true. For the incomplete check, a SAT solver might be called on the negation of the formula and the partial assignment. It could, for instance, be restricted to only execute unipropagation or abort its search of the predefined number of decision levels. For the semantic check, the SAT solver is run until termination. If it returns unsat, the partial assignment entails the formula since it cannot be extended to a model of the negation of the formula. The strongest test exactly captures the entailment condition on the projection, in which the relevant variables are universally quantified and the irrelevant variables are existentially quantified. A QBF solver is then called to check whether the resulting QBF formula is true, that is, whether the partial assignment entails the formula projected onto the relevant variables. We plan to implement our method and to validate its competitiveness on applications from weighted model integration, model counting with or without projection. For implementing the QBF oracle needed, we plan to investigate methods like, for instance, dependency schemes introduced by Sarma and Sider or incremental QBF proposed by Lonsing and Egli. We also plan to combine our method with the composition-based approaches and generate the DD and NF. That's all. Thank you for your attention.